Welcome and thanks for joining us today for the PNAMP Remote Sensing Forum. If we haven't met, my name is Amy Pohl and I work for USGS and the Pacific Northwest Aquatic Monitoring Partnership, or PNAMP for short.
And I'm Lauren Burns, and I work for the Columbia River Intertribal Fish Commission. Amy and I are leading today's meeting and facilitating the forum.
All right. So today's agenda. Actually, before I dive into the agenda, I'm running slides and polls today, and so I'm going to kill my camera so that things kind of run smoothly. So give me a second to do that. All right, so today's agenda. After I wrap up the welcome, we'll spend just a little time getting to know one another with a few live polls. Then I'll tell you about the online discussion forum that we're launching using the Microsoft Teams platform. After that, we'll have two presentations that we're super excited about. We'll have time for questions immediately following each presentation. And then at the end, we'll open it up for further questions and discussion if folks are interested. But first, a few tips on navigating the Teams meeting platform. So make sure you're muted when you're not speaking. If you're on the phone, you can use *6 to mute and unmute yourself. And if you're using your computer for audio, you can mute and unmute yourself using the microphone icon on the toolbar. Where you find that toolbar depends on whether you're using the browser or the desktop app. It might be fixed at the top right of your meeting window, or you might need to hover your mouse to get it to appear near the bottom middle of the meeting window. We invite you to use the chat at any time. We'll respond to technical issues as best we can, and we'll circle back to questions for the presenters during the Q&A. And for reasons we don't really understand, we are aware that some people can't get to the chat, and if that happens to you, I'm sorry. If you do have questions, you can always ask them out loud during the Q&A. All right, so it is always nice for us as facilitators, and I think also for you as participants, to know who's on today's call. So we're going to do that using live polling. You can get to the poll two ways, either using the link in the chat that Meg is going to drop any second, or maybe she already has. There it is. Okay. Or you can use the QR code. So keep in mind, you don't want to actually take a picture with your phone. You just want to aim the camera, scan the code, and a link should pop up that you can tap on. So hopefully you are navigating there now. And I'm going to pull up the results and see how things look. All right.
As expected, Amy, we have a couple that identify as aliens.
Yeah, I see there are others in the minority with me thinking they are among us.
Maybe we'll pull this through to the next forum meeting and ask a follow-up question about aliens.
All right, sounds good. All right, so the second question that we're going to ask is a little bit of an experiment. So we are going to ask you to drop a pin on the map to show us where you are, geographically speaking. And when we tested this, not everybody was able to get it to work. So we want a slightly larger sample size. So we're going to ask you to try it, and then we'll ask a follow-up question to see if you were able to get it to work or not. All right, so let's give that a try. I'm going to advance the question. And so here it is. Here's the map. See if you're able to drop a pin, kind of showing us generally where you are today. All right, at least one person has done it. Two people. All right, we have some success, it looks like. Okay, this is exciting. Results are rolling in. All right, we've got, I think, similar to last time. I'm wondering, I don't see any pins in Idaho. Last time we had, Richie was all alone in Idaho. You're not even in Idaho today. All right, so let's see how that went for people. So I'm going to advance the question. So did that work? You know, were you able to get that to work or not?
Yeah, not everybody. I am curious. Yeah, if you were having issues, maybe state if the issue was technical difficulties or your region wasn't represented on the map. Thanks, Richie. Appreciate that.
Yep. Richie, he is in Idaho. All right. All right. So, well, thanks for playing along. I'm guessing, I don't know, that it wasn't like a complete failure. The vast majority of people were able to make that work. We'll have to think about whether we want to use that going forward. I know it can be frustrating if you can't get it to work for you. So, all right. Get back to my slides. All right, so from conversations and past polling, we have heard from the community that at least some of you are interested in an online forum or discussion board. The idea being that you can have technical conversations in an open forum so that everyone can benefit from that exchange instead of it being concealed in an email thread. And Microsoft Teams seems fairly well suited to serve this role, and it seems that more and more organizations are using it, so we are going to give it a try. We've set up our team with 3 sections, or channels as they like to call them in Teams, one for Q&A, one for sharing resources, and one that we're calling meet and greet. So now I'm going to attempt a live demo. Wish me luck. All right, so this is the view from the desktop app. I believe the browser view is similar. If I click on Teams, you're seeing the teams that I am a member of on the left-hand side. And then if I click on remotes in the forum, if I click that little triangle next to it, you can see the channels that I just mentioned. The general channel is for general team reminders and posts, kind of a catch-all for things that don't fit elsewhere. We have the meet and greet for introducing yourself and meeting other members. Up at the top, I've pinned just sort of some general guidelines for introducing yourself. The next channel you see here is the organizing committee, but this is a private channel. This is something that you'll only see if you are on the organizing committee. And it's not top secret. We're mostly just using this to collaborate on shared documents. Questions and answers is a place to ask and answer questions. So to post a question, you would just click on new conversation. And from there, you can just type straight away. If you want, you can add formatting, you can add attachments, you can add emojis, GIFs, stickers, whatever you want. You can stick with plain text. And then when you're ready to post it, you just click this little airplane over here, paper airplane for send. And then when responding to questions, please try to keep things threaded together. So if I can use a different group as an example. You can see here's the original post, and Leslie has replied by clicking reply instead of starting a new conversation. That way we're going to keep our questions and answers together. The last channel is resources to share. And that's just a place for you to post anything you think the community would be interested in. That could be links to papers, websites, webinars, whatever you think. If we go back to the general channel, up along the top, you'll see there are also tabs in addition to posts and files. I've also created a space for recordings, and this is just linking to our YouTube page. And right now, this is our second meeting. So once this is over, we'll add this to the list, and that list will continue to grow. The other thing I wanted to point out was the README document. So it has descriptions of the channels. It also has what I'm calling netiquette for online discussion boards, and I encourage you to read through that before posting. It has typical recommendations about being concise, respectful, and on topic. But I did want to point out number 2, that before posting, you should check to see if the question you're interested in has already been asked. And you can do that using Control F or Command F if you're using a Mac. Again, I'll go here as an example. So up here, there is a search, but that's going to search really broadly. So we want to narrow it to just this particular channel's post. So up in the search, I'm going to hit Control F, and now you see I'm searching just the general channel. I type in my search term, hit enter, and then I get results on the left. So any post that, mentions that keyword. So that's a good way. I mean, right now there's nothing there, but hopefully as the forum, continues to grow and is being used, we'll have more and more posts. So it's nice to be able to search through them easily, and that seems to work rather well. All right, so going back here, I think the only other thing I wanted to point out, and it's also in the README file, is keep in mind that once you post, you can't delete it. You can edit posts, but you cannot delete them. And so as an example, if I go here, so this is my post with those guidelines. And if I click on this ellipsis, you can see that I have the ability to edit my post, but there is no option to delete. And then if I go down to Narayan's post, for example, you can see I can't edit his post. So that'll only show up if you are the originator of the post. Okay, I think that was the quick run through of teams that I wanted to share with you. Let's go back to the presentation, talk about how you join the team. All right, so to gain access to the team, you need to go to the Remote Sensing Forum project page at pnamp.org, and Meg's going to drop that link in the chat right now. But if you can't get to the chat, or if you want to do this later and don't have the link, you just go to pnamp.org, select the Remote Sensing Forum from the project drop-down menu, and then near the bottom of that page, you'll see there's information on how to join. Here's that same information, only larger. If you work for an agency that is part of the Department of Interior, if you click on that link, you'll have access to the team immediately. If you're not part of the Department of Interior, it's going to take a few more steps to get access, but you should be able to get to the team within 24 hours of initiating the process. If you have any trouble getting access, don't hesitate to reach out to me. All right, and now I'm going to hand it over to Lauren for another poll.
All right, thanks, Amy. Live demos are scary, but I think that went really well. And yeah, as usual, please sign up and share the resources widely. We're trying to grow the community. So thank you in advance. The next poll that we're going to be doing is getting more at the meeting topic, which we're kind of covering artificial intelligence and machine learning. So head to that link and feel free to engage in the poll and answer what's your level of experience or familiarity with artificial intelligence and machine learning, commonly referred to as AI/ML. Great, so it looks like we have answers coming in now. Decent amount of people that have at least heard of it, including myself. I haven't applied a lot of these approaches or built any algorithms myself. I'm also glad that newbies are here that maybe don't know a lot about it, but are here to learn. That's what the forum's for. Great. Not many people are advanced. I don't know who would classify as advanced, but we appreciate your guys' responses. All righty. So now we're going to move on. I'm going to be facilitating this main portion of the meeting. So as we mentioned, we have two speakers today. The first speaker is Kai Ross from Cramer Fish Sciences, and he's going to be giving a presentation on automated feature extraction, the trials and tribulations of extracting LWD, or as we refer to as large woody debris. So Kai, take it away.
Yeah, thank you everyone. Just making sure I'm coming through. You can hear me?
Excellent. You're great. Sound great.
All right, let me share my screen and switch to actually the presentation fully and swap to the view. So that looks good for everybody, I assume?
Looks good.
All right, so yeah, my name's Kai Ross. I'm a senior biometrician at Cramer Fish Sciences, and I've got sort of a long career working in the world of sort of remote sensing and this sort of programmatic analysis. My background really comes from, for this topic, from the world of forestry, which has been sort of embracing the world of LiDAR acquisition for a little bit. They were sort of, maybe ahead of the game in the world of natural resources on this sort of use of some of this stuff. So that's sort of the place that I'm coming from. But today I want to discuss sort of, as I thought this would be a nice topic to kind of intro the forum of, just a general overview of some of the trials and tribulations, some of the good, the bad, and the ugly of automated feature extraction, specifically through the lens of extracting large woody debris. It's really nice because it points out a lot of the difficulties that you're going to potentially encounter here. So that's really the overview I was going to give you guys today, is just this review of automated feature extraction techniques through the idea of trying to estimate or measure large woody debris in riparian settings. And the three kind of big categories I'm going to cover are going to be sort of pixel-based classification. This is sort of the old school methods. Point cloud techniques. So this is more the modern LiDAR approach. And then finally, what maybe the forum topic is actually kind of focused on a little bit more is the object-based classification that potentially pulls in this kind of sort of neural network bit. This is sort of like the buzzwordy piece for machine learning and AI, although I'll demonstrate that even the pixel and point cloud-based techniques still can take advantage of this. So pixel-based classification, this has been going on a long time. And basically the idea is that it determines a prediction for each individual pixel on some kind of raster that represents some image in reality or landscape. It's based on a variety of overlapping input, and by kind of doing the math on these overlapping inputs, we can deterministically convert that data into class membership. So the really standard example that a lot of us have probably seen before is the NLCD, the National Land Cover, right? So these are 30-meter pixels that are determined to be a variety of things based off of some cool algorithms that they've run. So this is the sort of basic idea of a pixel-based classification that I was introduced back in the day. But over time, things have really changed. So the idea of a 30-meter pixel, that's aggregating multiple features into one pixel. And nowadays, the resolution's sort of flipped. We often have sub-pixel resolution on a feature. So instead of aggregating multiple features into one, we've got the opposite, where we're having to aggregate multiple pixels into one feature. So although that's the good example, it's really kind of flipped the script in a lot of ways. Some other things I like to point out about pixel classification is that it's not limited to just sort of the wavelength imagery that we usually discuss. Topographic measures such as aspect, elevation, and slope can be incredibly helpful for doing models based off or in an attempt to determine tree species, for instance. Other environmental factors like annual precipitation, predicted shade, even time of day can make a difference on these things. So there's a variety of other factors you can work into your analysis beyond just the imagery, but the point is that there is some kind of continuous representation that you can have overlap with your imagery in a pixel-based scenario. So this is sort of like the big picture of pixel-based classification. And the analysis basically goes through sort of a pretty standard set of steps. So when we're talking about pixel-based classification, one of the first steps that you go through is a process, a pre-processing step. So this can be normalization and signal stretching. It can have edge refinement. I mean, there's a lot of work and a lot of science that goes into this. Like I've mentioned here, it's almost an entire field of science of itself. But just as an example, the goal here is to maximize the information contained within your data. And so on the image on the right here, you can see a landscape that is sort of a little washed out. It's not really taking advantage of the full chroma wavelengths to represent this. And so we can normalize, stretch, and enhance the colors and kind of make it pop a bit more. And this makes it easier for the computer to often sort of see the large changes or the gradients between the pixels that often drive these algorithms or these classifications. So pre-processing is often an important step. That's, the overall goal is to sort of maximize the utility of your information by sort of, normalizing or expanding it based off of what's missing or can be used. So this is a pretty standard pre-processing step with RGB imagery, for instance. Doing a color band, histogram, stretch, or enhance is what I'm showing here. Once you've got the data kind of cleaned up, the sort of initial strategy that you might approach would be unsupervised sort of classification. So these are often referred to as clusters or clustering. The two big ones that people often mention are k-means clustering or isodata clustering. These are basically asking the computer to look at the data itself and just sort of break the data according to how the data is arranged into a preset number of classes. So you, as the analyst, tell it how many classes, say, hey, break this into 8 classes for me. And it goes through the data and it figures out where to put lines in the data to make sure that there sort of minimizes within class variance, but maximizes the variance between classes. So it's sort of like a Jenks natural breaks, if you think about it from the Esri sort of symbolization point of view. But the idea here is that it's unsupervised, meaning I don't tell it what it's looking for. I'm not saying, fine, this is an example of a log or this is an example of a tree. I'm just asking it to break the data into clusters according to how the data is represented by itself. So that's where the unsupervised term comes in. This is as opposed to a supervised kind of algorithm. This involves training data. This was something where you highlight a whole bunch of features, you tell the computer or you tell the algorithm ahead of time, these are what these features are, and then it can use that to sort of build certain types of patterns, which it can then find within the other within the data set normally. So this is where you get to the very basic start of machine learning and AI. So I like to point out that one of machine learning really in this field, random forest models, right? So this is a bootstrap technique based off of iteratively subsampling your data, building up this cascading classification tree, and using data to inform its accuracy iteratively. So it's a good example of sort of a low-level machine learning approach that we get to apply that actually has really high results. Going towards the other side, you have something like Geobia, which is your geo-based, object-based image assessment. So that's full-on, e-cognition, TensorFlow style stuff. So the cool thing about supervised analyses, though, is that that training data that you use to build the algorithm basically automatically works as a sort of set of validation. So one of the nice things about these supervised algorithms is they often have validation built into the algorithm itself. So it's pretty easy to analyze. Otherwise, once you finish either doing a unsupervised or supervised pixel-based classification, you get something like what you see on the right here. We've turned the landscape into 5 or 6 classes, and that's the representation. Once we have this, it's not like we're done, though. There's still a final step of both post-processing. So this can involve minimum size requirements, sieves, neighborhood analyses. The idea is that, a single pixel of water out in the middle of nowhere probably isn't actually a pond. Maybe there's some rules that you can apply to sort of clean this up. And then once you get past the cleanup, then you can do some sort of validation to make sure that your model is actually doing what it should do, right? So that's sort of in a nutshell the pixel-based classification workflow. It's pre-processing, building some kind of algorithm or trainer to kind of classify your data, post-processing that data in a meaningful way, and then validating it. So for the world of large woody debris, what's RGB pixel classification get us? Pretty promising results, honestly. So you get good classification from unsupervised routines. And what I mean here is on the right, I've taken this RGB image that you can see on the left, and I've told the k-means clustering to break it into 8 categories. And I didn't tell it that those represented deep shade, deeper water, or any of that. I just said break the data into 8 categories, and then I renamed those categories as you see. And it's pretty impressive. Obviously, there's some serious overlap in what I'm calling LWD with some of the grass areas, right? But the pink pixels or the pink lines within the water channel are sort of natively seeing a signal about those logs in the water. There's some kind of reflectance in them that kind of the data itself makes them their own category when we're trying to cluster the data. So we're seeing some pretty good results here, but I'm guessing one thing that should pop out to your eye is the amount of purple in that image, the dark and medium purple. That's all shade. And while a useful category or an easy category to classify, it's not actually relevant for explaining the world, right? Shade is sort of a it's a condition, but it's not actually determining what's underneath that shade. Underneath that shade is water, is grass, is forest, or dense vegetation. And so this is one of the main issues that you can come to with sort of RGB classification in a lot of ways, is that this aerial imagery often has these shady pockets. And there's this is, like I said, an unsupervised classification using 8 categories. But what's cool is one of the things you can do with unsupervised classification is you can sort of use it as a data exploration. You can see what's available. So as an example here, I've taken, as you can see, these 6 images. The one on the top left I've taken 3 areas of shade and I've put little white bounding boxes on them. And the area of grass, I've put a black bounding box around. And then I've increased the number of categories that I've told the unsupervised classification to create. And what you can see is as we increase the categories 10, 12, 15, up to 25, those shaded areas remain pretty much red blobs. However, the grass area becomes more and more colorful to the point at 25 categories, it almost looks like TV static, like a rainbow static. And so what this is saying is that there's more sort of signal information, more variance in the information within grass than within individual pieces of grass, essentially, or the grassland area, than there is within all of that different shade. And I highlighted those 3 different separate areas of shade because 2 of them are channel spanning water and 1 of them isn't. So there's actually unique information in that shade beyond just that it is shade. And even after 25 categories, we're still not really able to pick it out, but there is information there. And so what this is telling us is that maybe single pass clustering won't cut it. So looking at an RGB signal, so this is a histogram, an RGB histogram, RGB going from top to bottom of those categories, we can see that shade actually has some strong data. There's a little bit of wide tail on specifically the RGB, the blue and green. This isn't nearly as peaked as the water. So there is data in this shade area. It's just very compressed compared to the breadth of the sort of signal for the other categories. And so what this means is there is still the possibility of extracting this data. We just have to sort of treat it separately, or in this case, go hierarchical. So you can cluster the shade clusters, or if you're thinking about this in the machine learning sort of training data sense, you'd build out training data sets for shaded categories, right? So just to give you an example of what this looks like, so here's 4 panels. The top 2 is the sort of normal classification. I ran the unsupervised classification, and it determined some shaded locations shown in gray. The next 2 panels, I've now extracted just the information from the shaded area, and I've reclassified it again using unsupervised classification and asked it to break it into categories. And you can see, particularly in the 3rd panel on the bottom left, that we were able to recover the sort of differentiation between water's edge and grass. So that kind of area between where it separates the channel in the shade, we're actually able to recover that by running this sort of hierarchical classification. And then finally, you can put them back together and sort of see how we were able to reestablish where the channel flows in this case, although there's some edge artifacts and some post-processing that needs to be done to clean it up. But that's the general idea here, is that you can actually sort of build in the, when you're running one of these unspecified or untrained classifiers, it's just looking for the signal in the data, and sometimes focusing in on a certain subset of that data will help you find additional signals. All right, so now that you have something that maybe you're happy with, we have to discuss validation. And so one of the interesting things about large woody debris is that it's not very prevalent on the landscape. I mean, it is in one sense in a sort of a count method, but as a percentage of the landscape, it's actually pretty small. And so this is where there's a lot of nuance in evaluating sort of categorical classification. And one thing I'd like to highlight here is sort of the difference between accuracy reports and the idea of Cohen's kappa, or quantity or allocation disagreement, any of these sort of ideas that kind of get at that, though. And the idea here is that, like I mentioned, you often have unequal feature allocation, and overall accuracy can basically mask this. So I've got a sort of a confusion matrix shown on the right here. So categories A, B, and C, you read a confusion matrix left to right, i.e. Category A was called category A 40 times correctly. It was called category B 5 times. That would be incorrect. And category C, it was called 0 times. So overall, we got 89% of category A predicted correctly. Now, if we look across all 3 categories, A, B, and C, if you sum up the diagonal, that is your overall landscape accuracy. So this model has 80% accuracy. Out of 100 points, 40 of them were predicted accurately. All right. So that's an important thing. But if my category that I'm trying to predict was category C, something that's not very prevalent on the landscapes, only 10%, this particular result here could show that it had 0 accuracy. But the way that you might report this would be a higher, an RMSE, or a root mean square error, or some kind of, overall accuracy measurement of either 80%. You could average across categories, which would give you roughly a 45% accuracy. But none of these really sort of describe the full kind of issue that we're having here, which is that we're totally missing this rare category. And so Cohen's kappa is an attempt to quantify this sort of disagreement with odd sizes by making a ratio that's defined to be sort of a improvement over baseline. So the idea is, if I know 90% of my landscape is forest and only 10% is prairie, let's say, a model that just says, oh, I know, it's 100% forest, that shouldn't be 90% accurate, right? Because we're totally missing out on one of these categories. So the idea is knowing sort of a baseline of what we think should be there, i.e. 90%, 10%, some sort of rough ideas. How much better do we do than just that baseline assessment? And this can be really useful when you're trying to assess something that's rare on the landscape. That being said, the easiest bet is just to report the full confusion matrix. I know it's really convenient to want to say that our model had an error or an accuracy of X and just state it with one number. This model is this good, done. But it's more nuanced than that. Models can be better or worse in a variety of ways. And so although it's really I understand the desire to report a single statistic, often reporting the full confusion matrix allows people to evaluate things in a variety of ways that could be useful. So how does this relate to getting down to large woody debris? Well, the good news is, okay, so we can take care of shade, right? That's a great thing. But in the case of LWD, there's another issue, which is we still can't see the logs underneath the canopy, and they exist. So if we're actually trying to count up some sort of floodplain, large woody debris recruitment or something along those lines, this could be a major limitation of a 2D analysis specifically for large woody debris classification. And so this kind of is a major roadblock or sort of a hurdle if you're interested in getting at that information, which is where you sort of bring in the next dimension. And so from here, we're going to discuss just go over some brief point cloud classification techniques. So we're going from pixels to points in space, X, Y, Z. So kind of an infinitesimal non-existent place that's defined by an intersection of three planes. And then we can use that to sort of represent the sort of, the world as we know it. So that background there is a nice example of a floodplain with some logs in the bottom left that you can see. So the first thing to point out is that point clouds come in many shapes and sizes, just like rasters. Maybe pixel sizes isn't you have a pixel size. You also have a sort of a point cloud density. So they could be accurate for very small, very accurate surveying resolution, or they could be flown from a fixed wing aircraft high above, which would not be able to yield the sort of resolution needed for some of these really small accuracies or some of these really fine analyses. So they can be derived from LiDAR. That's usually the place that we end up getting them, although this new technology for structure for motion has been very popular. That's where you're using sort of stereo ortho imagery to make a sort of overlay of the two images to kind of create a point hole, which also gives you this point cloud to analyze. So there's a variety of ways that they get made, but they are this sort of just XYZ components that get attributed with a variety of other information. So it's not just XYZ. For instance, LiDAR comes with intensities, point densities, scan angles, pulse counts. Structure for motion and other sensors can also return RGB as well. So there's a variety of things that you can pull into the data beyond just the XYZ locations. And it's important to point out that, it's 3D in XYZ, but it's not like a full 3D analysis in many ways. You're often projecting in a single direction. And so you have this sort of idea of projection shadowing, right? It's not like this sensor is somehow Superman flying through and seeing through roofs. So a roof completely stops the sensor, and there's no way to see what's underneath that roof without having another sensor on the interior that can measure it, right? So it's 3D in a way. It's a projection downward from the sensor, and oftentimes we can make some cool assumptions about how to fill in that gap in the background with ground filling algorithms and things like that. But it is important to note that without doing some extra work, you don't actually have the full 3D representation of your landscape. You have a sort of snapshot 3D representation. Another way to kind of emphasize this is this structure for motion versus LiDAR comparison that I'm showing here. Again, this shows that idea of structure for motion makes sort of a hole around the topography, whereas the LiDAR can kind of penetrate leafy vegetation. So you can see particularly on the left side of the profile where the line's been drawn over the planted shrubs, the structure from motion can't really see underneath the density of the shrub, whereas the LiDAR can. And so these are two different three-dimensional representations of the same sort of world, but they both rely on XYZ data. So why are we interested in point cloud classification? Well, the main reason is that there's a lot of use cases that have been really well documented. So water body detection and planar surface detection, we can do that. Here's a great example that comes out of the grass tools of a farmland scene where it's able to pick up buildings, trucks, and the kind of holding ponds, all based off of their sort of geometric representation, right? So it can find these flat areas by assigning these sort of planar algorithms and sort of assuming the geometry of things. And this works really well for and has, you know, the workflows for this have been pretty well established. Coming from the world of forestry, one of the things that I was just unbelievably psyched with once it started to become pretty usable was individual tree segmentation. So this is the ability to analyze a point cloud. And again, there's a certain geometry that we know happens here. There's this central bowl that's got a sort of a conical tendency, and there's a density, or a lighter density of points that sort of move out from that with a kind of shift top to bottom of an increasing diameter. Those three features allow us to basically come up with these individual tree segmentations, at least pretty well in the Pacific Northwest, where we deal with conifers. If you deal with, you know, sort of hardwoods with multi-branching stems and complex canopies, you know, these tools are a lot harder to implement. So it's just one of those, you know, there's reason to believe that there's some strength, but there's already some cracks showing. People like to point out phone poles and power lines. They're not too useful for the type of work that we're talking about in this forum. But again, it's that geometric representation. There's a very clear stick in the ground, and phone lines have a very parabolic curve that's very easy to model. So being able to detect them is pretty easy. And even like going further, there's, you know, this point cloud classification has been shown to do some really cool newsworthy things. Like I'm sure some of you guys have seen the extraction of ancient Mayan ruins in the jungle. The canopy layer there is so dense that hiking through it and ground covering it, people were missing 85% of these cultural sites. When they eventually were able to fly it with LiDAR, these square and rectangular structures were popping out like nothing. So there's a lot of reason to have some optimism about these point cloud classification techniques. Overall, the modeling follows a very similar path to the pixel-based classification. You pre-process your data in some way, and this could be sort of elevation thresholds. This could be pixel class evaluation. This could be sort of that pixel normalization and Z normalization to sort of make sure that you're taking advantage of the sort of full utility and information in your data, similar to the enhancement of color. But then it goes through a similar process. You either do some kind of unsupervised classification. This is like relying on geometry or thresholds, the stuff I was just discussing with the individual tree segmentation, or some kind of supervised classification that uses training data. So Canupo is one of the big algorithms that runs for sort of a training data on LiDAR data. And yeah, it does a pretty good job if you're able to get a good amount of training data. There's not a lot of variance between it. There's a lot of data that you have, and you've got, you know, high quality, really good resolution LiDAR data that doesn't have a lot of noise in it, right? So just being able to sort of filter out that noise as a first step is very useful. And this is sort of, you know, this is all really good news, but you'll find that most of the use cases are a little larger or smaller than what we're talking about today. My experience with point cloud classification, well, good, bad, and ugly. So first of all, I want to point out real quick that segmenting training data from a 3D point cloud is much more difficult than just highlighting rectangular features or the perimeters of features within a 2D image. 3D spatial manipulation with a mouse takes some effort. And the problem with these point clouds is, you know, when you're trying to build these training data sets, you're attempting to minimize the points that are included that don't represent your feature. So building a training for a barn would be pretty easy, but a log that's half buried on the ground represented some pretty finicky work just to sort of build out these training data sets. Unfortunately, based off of what we are seeing on these training data sets, that amount of error and noise that can be incorporated from sort of misattributing pixels can add up to be a big deal. The other issue that we found is, okay, so at the end we classify our point cloud, and now our points, we know them. We now have a beautiful point cloud that's classified with all the wood, and we know it. What do we do with that? Individual points don't really tell the whole story. We need to translate those points into something that's useful as a metric. We need to turn those individual points into logs. We need to turn those logs into diameters or sizes to be able to estimate volumes, right? So you're not done just because your classifier matches reality. Now there's this additional step of being able to convert the 3D world to something that you can actually use and report. And finally, an interesting nuance is you can have inconsistent data within sort of the one study area. So if you have a LiDAR data that was able to collect RGB data as well, so color information, often the color information is much less reliable underneath the canopy. So the laser is able to get through there and you're able to get the elevations, but the RGB stuff starts losing its quality. And because of that, you now sort of have bifurcated data in your model. You've sort of got the shade problem again, is essentially what you've got. And so again, you can train it multiple ways, but it's sort of a hard way to deal with it. So this leads to the final piece that we're going to discuss, which is object-based image analysis. This is where you're looking at regions or groups of pixels, and it makes these entire sort of areas a classification call. This is your e-cognition if you're used to the Trimble world. TensorFlow is sort of the bigger Google-sponsored AI neural network version. But this sort of idea of looking at an actual grouping of pixels as opposed to an individual. It's computationally costly, it's pretty cutting edge, and honestly, it can also be sort of monetarily costly. Some of the algorithms, there's not the best ones are not open source, and just sometimes having the ability to run some of these things in large scale requires you to maybe even schedule some server time to train some models. The overall goal, though, is that it highlights or bounds features as opposed to coming up with individual pixel color classifications. And so you can see here on the right, we've sort of actually highlighted the tops of these tree canopies. But it needs a lot of training data to build these. You'll often see training data on the order of 400 to 1,000 images per category. And there's a lot of nuance on how predictions can be made. So for instance, this is one that might be discussed by some of the other folks, but it's an interesting thing. Can you have overlapping predictions, and can you have inset predictions? So on the right here, you have non-overlapping predictions. If they did overlap, they'd all just be one canopy. But if you use sort of a different form of object detection, you might be able to see something like this. These are all trees, but you can see the examples of some trees overlapping with other trees or actually being inset within each other, i.e., do you detect the guy's logo on his shirt, or is it just a human overall, right? So there's this idea of segmentation and object identification that is sort of a nuanced topic when it comes to extracting large woody debris. So that's basically where we're at this point, is using sort of everything under all the tools we have to try to estimate these things. So I guess you're asking, does it work? And the answer is it kind of. It can be tuned to work well for specific circumstances, but I don't think we're at a place where it's as simple as just downloading the tools and running them for something like estimating large woody debris in a riparian setting. I'm going to point you to this paper, Estimating Coarse Woody Debris Volume Using Image Analysis and Multispectral LiDAR. It was 2020 in forests, and they point out, using a very, very well done study, they get about 75% completeness and about 75% correctness on their coarse woody debris classification on their field validated training data. So it's good, bad, and ugly. You can definitely get something, but it's not going to knock there's no home run story here. Some of the main issues that exist are limitations based on of RGB classification. It turns out multispectral LiDAR can help, but boy, it's costly and it's kind of uncommon and has its own set of workflows to work with. The pre-processing tricks, they're less effective with larger study areas. So the more area, the more stuff you have in your image in your study area, the less you can sort of stretch things to exaggerate things to make things happen. If your study area has a full rainbow of radiance in it, then essentially color enhancement's not going to do much. And finally, seasonality is super tough. Plants are super tough. Animals are tough. This stuff's really hard to categorize because it's not very consistent. Atmospheric changes, the time of the month, the time of the day, the amount of humidity in the air can all potentially change one acquisition to another. Similarly, changes in physiology, the time of the year can have leaf on versus leaf off, new bud growth versus no bud growth. This can completely change the color, texture, and shape of plants that you're trying to classify. This starts to increase the amount of training data you need and also starts to blur the categories. So some final thoughts. Automated feature extraction is a fast developing topic. What's possible now was basically a joke not too long ago. I mean, we now have sub-pixel resolution on logs, neural networks that can perceive shape, texture, color. So it's really moving forward. That being said, the world of natural resource management definitely warrants skepticism. No two places are identical. It's sort of the law of geography, right? And what works for one may not work for others. So it pays to sort of be a little slow to enter the game on some of these things. That being said, I don't think this is one of those places where, hey, just because it's not perfect, we should march forward. It's more nuanced. Everything has a trade-off, and a deterministic accuracy of 70% might be favorable to some kind of really accurate 98% human accuracy if you're aiming to do thousands of acres and you can automate it, right? So just knowing the trade-offs, the ups, downs, the pros and cons of the tool at this point, I think is probably the most valuable thing, because there isn't sort of a canned solution that's always going to work, and it's going to depend quite heavily on your study area, your goals, and what kind of data you're going to be able to potentially use to make these assessments. So with that, I'm happy to take any questions. If I know that these live forums can be a little hard to kind of think through, so if you come up with this later, feel free to email me, and I'm happy to continue the discussion there.
Wow, thank you, Kai. I could relate to a lot of the challenges that you brought up in your presentation. I've definitely experienced some analysis setbacks related to shades, so thank you for the really great information and tips about hierarchical analysis. In general, that was a really great overview about classification techniques, and really impressive what you and your group at Cramer have been up to. I don't see any questions in the chat, but if anybody wants to raise their hand and ask a pointed question for Kai, either drop it in the chat or raise your hand.
Yeah, I see Connor, you have your hand up. You want to ask a question?
Yeah, I'd absolutely like to ask one. You guys can hear me okay, right?
Yes.
Coming through great.
Okay, perfect. I was curious, what's your opinion on using multispectral imagery, not necessarily multispectral LiDAR, but multispectral imagery in the sense of near sensors, red edge, and dedicated RGB in order to try and pull out some of those classifications? Do you feel like there's some good merit to that?
Oh, very much so. Specifically, the NIR is a huge help with dealing with the shade bands. So being able to be those shade categories. Basically, the more information that you can throw that's concurrent, the better the classifiers are going to have. And that's one of the cool things about the machine learning style classification. So as an idea, a random forest model, if you include those bands along with RGB and they provide no additional benefit, then it just won't use them, and the variable importance plots will show that they weren't useful in the classification. But from my experience, the more signal that you can have overlapping in space, the more sort of representation of data, the better the classifier is going to be. And oftentimes it comes out in places where you weren't potentially you wouldn't maybe guess that it would be an important difference in things. So we all know, or it's pretty common that the near infrared is used for differentiating conifers and hardwood species in the forestry setting, but it can also do some pretty impressive things with non-woody versus woody riparian vegetation.
Great. Yeah, that's kind of what I've seen from the research that I've done on it as well. I was just kind of curious what your take was. So thank you. I appreciate that.
It looks like Richie Carmichael, one of our organizing committee members on the Remote Sensing Forum, also dropped a comment into the chat that I'll just read aloud to document for the meeting recording. So he says, one of the biggest issues with unsupervised classification, such as k-means, is that it never gives classes such as water and bare earth the same class value from site to site, forcing me to change it later on. Any thoughts on ensuring that cluster class values stay the same across sites? For example, water always equals 1, bare earth always equals 2, and rocks always equal 3, etc.
Gosh, that is definitely a frustration in the world of unsupervised classification, because it doesn't even know like if there are going to be rocks or water in one of them. One of the things I've been able to do if I'm working in a consistent area is you can build sort of a small area that you can classify that is easily interpretable. I'm talking individual pixels, and you can use that as a crosswalk table. I've done that before. But no, that's definitely a hard one. Is different tools also, I'll mention, have the different implementations of k-means will also do what you're describing, or what Richie was describing, separately. So the Saga implementation will be a lot more consistent, I've found, in numbering sort of how you'd hope, compared to some of the others. But individual algorithms definitely sort of just choose, I guess, what they feel that day on how to kind of label those categories. So that is a very valid point.
All right, thank you, Kai. In the interest of time, let's move on. We have one Menti question that we're going to use while we have everyone here. So please go to that link again. It should be live. So this question, before we move on to the next speaker, is when evaluating the feasibility of incorporating AI/ML, which again is artificial intelligence and machine learning approaches into post-processing workflows. So yeah, what's the biggest factor for you or your agency? Is it time, money, expertise, or all of the above? All righty, so we have some answers coming in. Yeah, this is pretty much the answer that I expected, all of the above. Money is definitely a factor, and Kai alluded to that. But there's also a substantial startup cost in referring to the time investment. So it takes time to become knowledgeable and become proficient, which is one of the questions that we asked early on not only these techniques, but also coding and using these different software. Because if you're not proficient in multiple coding languages, you're going to go with something more standard out of the box, like eCognition, which costs money. And also there's a learning curve. So thank you all. These questions are super helpful, and we do frequently go back and reevaluate the number of people answering and use these to kind of guide future remote sensing topics. So we appreciate your responses. And as always, feel free to reach out to Kai if you have any other questions. And this meeting was recorded. So now we're going to be moving on to our second speaker, Rikeem Sholes with the U.S. Fish and Wildlife Service. And Rikeem is going to be going over some of his approaches to using technology in fish population monitoring. So his title is Burgeoning Technology in Fish Population Monitoring. So Rikeem, take it over.
Hi guys, can you hear me?
Yep.
All right, I'll
Thank
keep
you.
my camera on for the introduction, but then I'll turn it on for the rest of my talk, just because it's easier for me. All right, so my name is Rikeem Sholes. I'm a fish biologist and new PhD student at WSU Vancouver. I work out of the Columbia River Fisheries Office on the hatchery assessment team. I'm also just kind of the office tinkerer. I take care of our pit arrays. I'm the drone pilot, and basically anything that involves electricity is the type of stuff that I do. So I have every 12-year-old boy's dream. And today we're going to be talking about burgeoning technologies in fish population monitoring. So just as a general outline, I'm going to talk a little bit about the single board computer that I built for a lamprey monitoring project out in Warm Springs. And I'm going to transition that into an ongoing machine learning project that I have going, monitoring bull drop populations in Oregon.
And Rikeem, I can't see your slides yet. Are you sharing your screen?
I'm going to share here.
Okay, thank you.
Can you see me now?
Yep, you're good.
Okay. All right, let's go. All right, so let's get started. So you can see from this picture here, this is Warm Springs National Fish Hatchery. It's in Warm Springs, Oregon. It's got basically this dam here to prevent salmon from going upstream and kind of forces them through the hatchery, so they can be counted during spawning time. And in 2017, we realized that this dam just wasn't really working out for lamprey making it back up. So we installed this kind of lamprey passage system. It's just this aluminum or probably stainless steel slide that you can see right here that lamprey can use to bypass the hash rate and make their way up. So I was a new biologist a few years ago, and they knew that I had some experience doing camera stuff, and they're like, "Oh, Rikeem, we need you to count lamprey as they come through this thing." So I had to figure out a way to monitor them. So of course, I went with the easiest solution first. Started off with just a standard DVR and underwater camera. Obviously, it needed to be waterproof because you have water moving through that lamprey passage system. And we quickly figured out in the pilot year that wasn't going to work out. The DVR that we were using, it was very hard for us to differentiate moving water from moving lamprey. So we just ended up with tons of data. And I really would feel bad for any technicians or volunteers that we had to look through all that data in the hopes of seeing some lamprey. It ended up being almost 24 straight hours of data. So we figured out that we needed a custom solution. And what did we come up with? Lasers. Okay, so not really lasers. I like to tell people lasers because it catches their attention. We actually ended up using beams of infrared light. I'm probably going to say lasers a few more times during this because I'm used to saying lasers, but just know that I know what a laser is, and I know this infrared beam is not a laser. One day my supervisor came into my office while we were trying to figure out a real solution for this, and he's like, it'd be cool if we could have a camera trigger as the lamprey were crossing, like a beam of light, like the one that is basically a safety catch on your garage door opener to stop it from crushing you. And we kind of laughed that off. But I worked with some people who did some single board computer stuff up in Alaska. And I'm like, wait, I think I might be able to make that happen. Luckily, these lamprey passages have laminar flow through them, and the lamprey's body sticks up above the water. So we could have this actual laser system work out. And unluckily, or maybe it was luckily, I can't really tell, but we got furloughed like 3 weeks later after he had this suggestion. So I ended up with a lot of time and not very much money. So I'm like, all right, I'm going to try and make this thing, but I'm going to try and make it on the cheap. And this was my first prototype. So this is a Raspberry Pi. It's a small single board computer. It's basically like a fully realized computer that runs off of a Linux distro. It runs off a Debian, a downstream of Debian called Raspi or Raspbian. It's got a USB 3 ports. It's got Ethernet cable. It's Wi-Fi capable. It's got HDMI. You can connect almost any sensor that you can think of to this thing. As you can see right here, I have infrared sensors. So these are two infrared sensors. One is a receiver and one is a transmitter. And there's a beam of infrared light going in between these two. And also up here is an infrared camera with the lights on it. So this has to happen in the infrared range. Some of you probably know that lamprey mostly move at night and they're negatively phototoxic. So it has to happen in a range that they can't tell we're looking at them. Basically, we need to be spying on them. And this was my first test. And I was super excited that this actually worked because I had only been programming for like a few months at this point. So I wasn't sure that any of this was going to work. And then as you can see, just pretend that SD card was a fish. So as you can see, that SD card came through and this light came on, letting me know that it was actually that the camera was actually recording. So I'm like, okay, well, this works. Now I just need to waterproof this whole thing. Okay, so I found a company fairly quickly that made waterproof casings for Raspberry Pis, and this was my version 1. I had to modify it a little bit to have some openings for the wires. I found these waterproof PG glands and made an opening for the camera. Luckily, the size for the camera fit perfectly into a PG gland. I thought this clear top cover was really cool at the time. I ended up changing it out because the red blinking light on the Raspberry Pi, I was afraid it was going to scare away lamprey. But yeah, so this is it installed. This actually isn't at Warm Springs. This is our second one installed at a different place on the Oregon coast. But yeah, it's a small 5-board single board computer. It's Wi-Fi capable, so I can download the data remotely and change the code remotely. It puts off 1080p HD infrared video, and as I said, it's completely waterproof. So we got back to Warm Springs and we decided to install this, and this is the array of technology that we use to count these for the last few years. So the first is the camera that I just showed you. So this is lamprey this is the dam here. Lamprey will come up over this edge, and the first thing they'll hit is that sensor. They'll cross the brake beam in there, and the camera will start recording for 30 seconds. As long as that beam is broken, the camera will keep making new recordings. Then I installed the backup camera. Basically, I just kept the waterproof camera that we had from last time because, to be honest, I wasn't super confident in this when we first built it, and I'm like, there should be something there in case this thing doesn't work. So this thing runs 24/7, and it actually just acts as a backup. Like sorry, it's a verification. So if I see a lamprey come through here and I see it go through here, I know it's at least going in the right direction. And I also designed a water sensor. So around that same Raspberry Pi model, I designed a water sensor. I can get into the operation of that a little bit later. Unfortunately, this part of the hatchery is in a place where hatchery staff don't come to regularly. It's away from the raceways. So if the pump that powers this thing goes off, it could be off for a weekend, it could be off for days, and nobody comes over here, and lamprey aren't going to come through this if it isn't wetted. So I needed to have a way to tell if it was off. So basically, I built a Raspberry Pi system that would continuously poll water level, and if that level changed to a point where it wasn't enough to run through here, it emails me and lets me know so that I have a record of when it was on, when it was off, and I can call the hatchery manager and be like, hey, you should go check on this to get it fixed. And the last thing that they'll hit is a pit detector. Some of these lamprey are pit tags, and we can extrapolate those numbers out between untagged fish to tagged fish and get a population estimate that way. Okay, so we hit on this a little bit. Why not just buy something off the shelf? The biggest thing for me was cost. I at least for the prototype, I used my own money to build it, so it was going to have to be fairly cheap, especially with me not having a paycheck at the time. So in this whole device, I was able to put together that whole device for roughly $60. Most of those sensors are super cheap. It takes a fairly little amount of time to pot them in and make them waterproof on your own. Whereas the cheapest camera and DVR setup that we had cost about $400. You could get into some higher IP cameras that will do a lot of this stuff, but you're talking hundreds just for the cameras, and for the analytical software, that's maybe hundreds or maybe thousands of dollars. And you could do a lot of this, as I said, without spending that much money. The video on the lower end tends to be fairly low quality, whereas I can get really decent quality video if I really played around with the settings for my system. The needs for power are a little bit more. You have to power the DVR, and you also have to power the two cameras, and both of those need 12 volts. I don't remember the amperage. But my system only requires 5 volts and it's 2 amps to power the whole system. And that's important in case we ever decided to put these in a remote location where we're just running off of like a battery bank or a solar panel. You want to have that power usage low, so you're not just draining your system. And also you have fewer triggers. Most of these DVR systems and a lot of IP cameras are dependent on either a physical trigger or a physical trigger or like I showed with the motion sensing. But with my system, you can have a high variability. You can have a million different triggers, because like I said, you can connect almost any sensor to those Raspberry Pis. So this water sensor that I mentioned, I was actually really excited when I saw this thing. It costs about $15. This obviously isn't my hand in the model that's from Adafruit. It's a hand model. I wish my hands looked like that, but it's a really cool system. I thought about using water sensors before, but the typical water sensors use connections. They use a conductivity sensor to detect water, and those can get scaled up, especially when you're using river water over time and give you false readings. But this one is fully enclosed. It actually uses refracted light to determine if water's there or not. And it's a really cool design. So it has a light emitter and a light sensor. And as the light is emitted, if this area is covered with water, the light will actually refract back in at a 45-degree angle, and then refract again off the other side, and then hit the receiver, and it'll register that as a 1 signal or an on signal. And if that area outside of the sensor is ever covered with air, the light actually refracts out, and the sensor will register that as a 0. So and from there, it's a pretty easy bit of code. I think this bit of code might be like, less than 20 lines long, and it probably doesn't even need to be that long to actually sense this change in voltage, and then turn that change in voltage, and then set in motion a series of events that emails me and says, hey, this is dry, call somebody. And then once it becomes wet, it lets me know when it's wet again. So I just want to show you guys some results. So obviously, like I said, this is all in the infrared range, so you'll have to pardon me for this kind of monochrome color. So this is at Warm Springs. This was their first detection 2 years ago. The lamprey is obviously moving this way. It doesn't know that it's being watched right now, as far as we know. So the camera system doesn't affect it, and it goes about its merry way. And this on the right side is actually a top down. The lamprey is coming towards the bottom of the screen, and they'll go into a small trap here. This is the first time that they had seen lamprey in the system in probably about 10 years, if I'm remembering correctly. So they were super excited to finally get this video. This is a project we did with USFW after this project worked out fairly well. All right, so one of the side effects is that you actually do end up getting lots of other wildlife. This was down at that same project on the Oregon coast. And this bird was there like every day for like a month. I don't know what he was looking for, but he would hop in and out of the sensor every day, and we were waiting for lamprey to come. So he was kind of the bane of our existence for a while, but now it's just kind of cute. And this mink, I believe it's a mink. I'm not a mammologist, and I'm not an expert here, but it looks like a mink to me. Came through, and I thought that was pretty cool. So I love showing people these videos. Okay, so I'd be remiss if I didn't talk about some of the unforeseen setbacks and some potential solutions that I have in mind for some of them. One of the biggest one is that the Raspberry Pi is Wi-Fi capable and can be connected to a Wi-Fi signal, but in a lot of these hatcheries, the Wi-Fi signal is fairly spotty. I don't know if any of you are hatchery folks, but they tend to be isolated, which means your cell phone reception is going to be kind of sketchy, and that means your Wi-Fi signal is going to be a little bit sketchy as well. The good thing about this system is that it records directly to a flash drive. It records to a 512 gigabyte flash drive, and it always records regardless of if it's on the internet or not. So it's usually just a matter of either waiting or having somebody reset the Wi-Fi hotspot to actually be able to access the data. Or occasionally you might just have to drive out. Warm Springs is 2 hours away, which was why I did this originally, because I got tired of driving 2 hours. The other big thing is that you have the occasional false trigger due to scale buildup, obstructions, and higher than normal flow. Higher than normal flow really doesn't happen that often because they're pump dependent, especially the one at Warm Springs. The one on the Oregon coast isn't. And if that level goes above the sensor, obviously that infrared beam is going to be broken. It's just going to constantly trigger. Luckily, the files are fairly small, and it would have to trigger for weeks before I filled up 512 gigabytes of USB space. But unfortunately, that can end up with you having hundreds of triggers. Also, sometimes scale will build up if it goes above it once, and then you have really hard water, or there's just a bunch of gunk in the water. It'll obviously block that obstruction, or it'll obviously block those sensors. Another big thing is like wildlife, like spiders at Warm Springs. That's a big problem. We have spiders build nests in front of the sensor all the time, and then it just triggers constantly, and I have to go clear them out. So some solutions that I come up with. E-tape levels. So this is a really cool. Once again, these are my hand models again. So one thing that I thought was really cool is usually with these E-tape levels, it used to be just a conductivity sensor at different levels to tell you if water sensor level was changing. But this one that I found is fully enclosed and actually use hydrostatic pressure. And my idea was to just have it constantly poll water level, and just keep an average over, say, 30 seconds. And then if that average ever changed by maybe 30% or so, you could probably be sure that that was a lamprey coming through, disturbing the level of the water, and then you could have a trigger on that. Uh, and this was another one, also, once again, not my hands. Sonar level, I'm not really sure if sonar will work out very well. It could end up being radar or lidar, but all these sensors are still pretty cheap, and they do the same thing. To do the same thing, where it would constantly just pull water level, uh, keep an average, a reference, and then if anything changed, deviated from that reference by a certain amount over a short amount of time, then it would start recording as you could be pretty sure that that was something moving through the system. But all these are more or less physical triggers, and one thing that I've really been looking into, and we'll transition into the machine learning part of it, is using computer vision instead, because it takes the physical trigger part of it away. I've had enough times where I've had these erroneous triggers that I started looking into computer vision for this project. For those of you who knew, I'm going to apologize, because a lot of this is going to be kind of old hat for people who have experience in this. But basically, this technology teaches the computer to recognize features in an image. It will remove or minimize the need for those physical triggers, and it's becoming much easier and cheaper to implement. So some of the ongoing and recently completed CV projects that I've worked on since I've started looking into this technology is so as part of my PhD research, I'm developing a model to identify the degree of odor deformation in hatchery-raised fish. We're finding that their calcium carbonate composite is different, and we have some evidence that shows that's leading to it's affecting their fitness. It's affecting their ability to rehome and just hear, and their real taxes, their ability to right themselves in a stream. So that's mostly what I'm studying. So I'm developing this model that'll recognize the degree of it through microscope photos. Last year, I worked with an AI company to develop a model that tracked population changes for commercial insect production. It's a little bit hard to tell what's going on here, but this is just basically their enclosure. This is some fake green foliage back here for them, and these little brown spots are the insects. And we were hired on by this company to keep track of their populations, and make sure that just show how they were growing. These insects were going to be used for fish food, for commercial fish food. And the one that I'm really going to go into is this ongoing bull trout restoration project that involves that we're doing in Oregon right now. It involves fish going through a weir. We track them as they move up through a weir. And in this project, we're tracking bull trout, kokanee, rainbow trout, and that's all the model. That's all I have at the model right now. It's my current baby, so it's my current thing that I'm working on. So this convolutional neural network is basically just designing a way to recognize these features, and it goes from the features of a fish, and it goes from low level features, which may just be, you can see these are lines or color changes, and then developing those features that you get as you move further and further through the network. It'll get to the point where it'll start, instead of just lines, it'll start recognizing, hey, maybe this curve on the caudal fin, or maybe it'll recognize this curve on the adipose fin, or it'll start to recognize lateral lines. It'll start to put some of these features together and give them weight to determine if those are the features that we're actually looking for. And then some of these higher level features are, yes, it's recognizing the whole caudal fin of a fish, or it's recognizing the whole head of a fish. I think I might have called this the caudal fin. I know it's the dorsal fin. I apologize. So, like I said, the purpose of the CNN is to classify images or portions of images based on its features. Think of it, I like to tell people to think of it like a child's brain. As children learn, they start to associate certain features with labels. They see a wet nose and wagging tail, and eventually they learn that that's what adults call a dog. Now as they learn, they may make mistake. They may mistake other things with those features, like they'll call a wolf a dog. But as they grow and get more examples, their recognition algorithm gets more and more refined. And that's essentially what we're trying to do here. And just for those of you who are experienced, just so you know, I'm using YOLO version 3 for object detection in PyTorch. YOLO doesn't stand for you only live once. It stands for you only look once. And that's basically just the object detection algorithm. And PyTorch is just a library in the Python language that facilitates deep learning. And this at the bottom is an output. This was one of the final outputs for an actual image recognition, where it actually successfully recognized the bullet cloud as it was going through. So one of the first steps for anybody who's done this type of work is realizing that, you know, you have to deal with your data. Luckily, this project had been going for a few years before I started, so I had a bunch of videos like this of bull trout just kind of hanging out or transitioning through the weir. And I needed this. So I needed to convert this to images so that I could actually train my model. And you know, we have gigs upon gigs of this type of data. So it was a simple task to build a Python script that took this video and spit out individual frames from each video. So I ended up with something like this. I ended up with just, you know, hundreds upon hundreds, if not thousands upon thousands of these flipbook pictures, where most of these pictures look very similar, you know, because it's just taking frame after frame from the same video. And this is great. This is great. This would be great data. But you need, as most of you probably know, you need to give a model a varied set to train on. You want to prevent overfitting. So as great as this was, it was really only good for me to get reference protos for my training set. But I needed, number one, to vary and get more quantity out of that training set. So that yeah, it wouldn't just overfit at the end and only learn the questions that I provided to it. So there's this great thing in CV that's called data augmentation, where, you know, usually when you're building a model, you don't want to just make up data, but in the visual realm, you really can just make up data, and it's amazing. So I made another script that took some of those reference photos and did these augmentations to them. So you can see here that this data it's a little fuzzy, it's a little grainy. I thought that it would be useful to give it that graininess on some of the photos, because, you know, you're not always going to have crystal clear water. So it needed to know how to see those fish when it wasn't crystal clear. Also, I gave it a few different orientations of fish, right? So I twisted the photo a little bit so that it wouldn't always expect a fish to come through going upstream completely horizontal, because that doesn't always happen. Fish aren't always doing that. And I wanted it to still recognize a bull trout as it was doing that. And this is a combination of both. This is close to the original orientation, where it's actually heading upstream. The other two are flipped. And yeah, like I said, you know, essentially what you're doing is you're creating a fancy regression. So you want your data to be generalized as much as possible to make sure that your accuracy is high. All right, so you saw that I showed the end result. I'm basically at the stage of this model where it's recognizing all three of those categories of fish just to a high enough degree that I started doing this project because I felt bad for the techs that had to look through hours worth of this data. And it's high enough that I feel confident that, you know, it's doing at least as well as our technicians would, and much faster than they would do it. So they can move on to doing things that would help them in their career later on. But I still have some work to be done. Obviously, I need to move over to making predictions on recorded video. You know, that's the medium that we have coming back. So it should be a short step to going from making predictions on photos to making predictions on video. And then ideally, so that's all I would need to do to help the to help the bull trout portion of it. But for other portions, like the lamprey project, I would want to make recordings on live video. Once it's making predictions on live video, it's an easy step from recognizing that there's something on the video, classifying it properly, and then starting a recording based on that classification. That's where I really want to get for recognizing lamprey, so that I can take out some of those physical triggers. And the last step will be optimizing this model for small scale equipment. I really enjoy the Raspberry Pi model that I've started on. I'm not sure that that's the single board computer that I'll stick with, just because it's a little bit limited. But even for just a nominal increase in fee, if I went up to somewhere between $100 and $200, I could get a single board computer that has comparable power draw, but also is optimized for machine learning, for actually making those predictions quickly. And this is, I found a video of my final goal. I know these are birds. I know we're fish. A lot of us are fish people, and we have like this kind of weird East Coast, West Coast beef with birders. But this is a company called BirdBot that actually is designing the algorithm, design this algorithm to recognize birds that basically does the same thing that I want to do. So that's hopefully in the next few months I'll be able to get here. All right, and that's almost 30 minutes on the dot. So yeah, thank you guys very much. If anybody has any questions, please let me know. If you don't think of any questions right now, here's my email address. Feel free to contact me anytime. I love nerding out about this stuff. And if you're an expert at it, especially, and you have some suggestions that might help me, please, I'm more than open to making any changes I can for version 2 or 3 or 15, wherever I am on my project. So yeah. Thank you, guys.
Awesome. Oh gosh, sorry. Thank you so much, Rikeem, for agreeing to present for the forum.
Okay.
Sorry, we got a little bit of feedback.
Okay, you hear me?
I just put you on mute really quickly, just because I'm getting feedback from one of your speakers. So again, thank you so much for agreeing to present with the forum. And that was really nice of you to spend your personal time and money to come up with a tool for the technicians. I'm all for creating low cost solutions that save you both time and money. So thank you for providing us with a couple of really cool demonstrations on these lower cost tech solutions for, aquatic and fisheries projects. So I'm going to open it up if there's any questions, and I'll unmute you now. Or maybe you have to unmute yourself.
How's this? Is this better?
Thank you.
Sorry, I don't know what that was about.
So we have one question in the chat that I'll just read aloud so that we can document it in the video. This is from Ryan Bassick. He's commending you. This is excellent innovation. What has been your experience with the River Watcher units?
Oh, yeah. So I actually hadn't heard of River Watcher. I gave a similar talk to this, just talking about the first section of it a few weeks ago, and somebody brought them up to me. They're doing cool work. They have some really cool equipment. I ended up going and looking it up after they talked about it. I don't have any connection with them. Like I said, I'd never heard of them, but really interesting stuff that they're building.
Great, thank you. Are there any other questions? Richie Carmichael dropped a comment and possibly a question into the chat. So thanks, Rikeem. Great presentation. Looks like he has some advice. One word of advice where we have success in training neural nets for identifying organisms is to import pre-trained weights from TensorFlow or Google API from other types of speciation/initiatives. That helps speed up our training tremendously.
Yeah, for sure. I've done that in some other projects as well. It does help a lot. I think I kind of took the brute force method to this just to keep myself busy. I needed something to do. But yeah, thank you, Richie. I appreciate it.
Yeah, definitely a super productive use of your time.
Yeah, it was a pet project that actually turned into like a large part of my job. It's life's weird like that sometimes.
No, I totally get it. Create the job you want. So if there aren't any more questions, we have one final question. Oh, Kai, you have a question. Go ahead if you want to unmute yourself.
Yeah, I had a question, but also maybe some good news maybe for you. So once you built out your sort of image process, did you go through the bounding boxing them somehow, or did you just feed those whole images? And did you find a a nice way to go through the bounding box process?
Yeah. So the bounding box, I do. I can send you, if you're coding in Python, I can find you something, because there are so many examples. I did use bounding boxes, by the way. It got infinitely easier once I started using bounding boxes, but it takes a long time to find a process that works well, and then take that data that you get from the bounding boxes and incorporate it into the actual code. And if you want, I can send you kind of the program that the program that I use, but just know that you're going to spend a lot of time just like clicking twice on photos, just like showing it both corners, so that it can actually automatically do it.
Yeah, I think I'm in a similar boat, but it's always interesting because I feel like a lot of times people still defer to sort of human derived, solutions, which it's like I feel that same way with the with text. Like having somebody draw bounding boxes all day seems like a horrible assignment. So the other thing I was going to mention is that the next step that you wanted to move forward is going from that image to video, and oh man, that's going to be an easier step than you think, and I think you're going to be real pleased with your results.
I hope so, because getting up to this point has taken a lot of trial and error.
So yeah, if feel free to reach out if you're having any trouble on that one. I think you'll be able to get that real quick though.
Will do. Thank you. I'll definitely do that, Kai. I appreciate it.
Alrighty. And I just want to note that if this is a question that, somebody has brought up here, it's likely relevant to the larger forum. And I encourage Rikeem, if you haven't already joined the forum, to first join the forum, and then second, share that resource in the post. And that way we can more widely distribute the resource and get it into the hands of others that might need it.
Great.
So thanks again, Rikeem and Kai. Those are really great presentations. I feel like I'm going to need to go back through on YouTube and watch one more time to fully digest. But we really appreciate you coming to present for us today. We do have one final Mentimeter poll before we wrap up this second meeting of the Remote Sensing Forum. So if we could, please follow the link. So the final question that we have for you, we'd like to get some information on our audience. So how do you envision AI/ML could be incorporated into your current work? So this could be any aspect of artificial intelligence or machine learning. What I envisioned here was, we could use machine learning to identify trees, identify large wood, identify boulders and streams. So we'd just love to hear from you, our audience, if you have any ideas or what your interest might be, and we'll use that to invite future speakers. All right, so we're getting a couple of responses. Restoration, tracking, habitat feature extraction. All right, restoration monitoring, invasive species mapping, landscape quality, land cover classification. Yeah, more fish monitoring and ID. Increasing spatial scope of monitoring assessments, habitat elements. Okay, so again, large weighted debris, trees, stream bed substrate. Great. Yeah, these are kind of all on par for what I was expecting. And it's great to hear that there's a diversity of needs from the representatives that are on the meeting today. We do just want to let you know that because there's such a large interest in this topic, we're planning to continue this this meeting topic into our September meeting. So we've already invited and lined up a few speakers for our September meeting that will also be talking about machine learning, automated feature extraction and classification. But please feel free to always send names our way. We're always looking for speakers and additional people interested in the forum. So again, thank you for joining us. And I just also wanted to say, I think all of you know that this meeting is being recorded and it will be linked in the Remote Sensing Forum page, the link to the video on YouTube. And I'm sure you're sick of hearing this from your kids and coworkers and people online, but hit that like and subscribe button. And please feel free to engage in the discussion board in Microsoft Teams. Amy, did you have some final comments?
Sure. Yeah. I just also wanted to thank everybody, both speakers. Those were awesome talks. I really enjoyed them. Thanks everybody else for participating and being here today. I'll send an email to the listserv later this week with the link to the meeting recording. If you're not on the listserv but you want to be, Meg will drop that link in the chat right now. And that link's always available on the PNAMP project page at pnamp.org as well, or the remote sensing project page. Our next meeting is September. I think Lauren already mentioned that. I'll send a save the date and a calendar invite once we have an exact date. If you have questions in the meantime, feel free to reach out to Lauren or myself. And I think that's it. Anything else from you, Lauren?
Yeah, I don't think so.
All right, great. All right, well, thanks so much for sticking around to the end. Enjoy the rest of your day.